Hey guys, this is Sean from Alexander Tutoring, and today's topic is related rates, something I think you are all working on right about now, something I struggled with a whole bunch the first time I saw it. The good news is I have a system for solving these problems that works literally every time. All you got to do is follow my steps, and it will guide you to the right answer every time. It's pretty incredible. So here's what we're going to do. I have an example problem here, and this is the classic cone problem. Every class I've ever seen has at least one related rates problem with a cone in it, okay? So reading through this problem, you've probably seen in your class, a conical paper cup is 10 centimeters tall with a radius of 10 centimeters. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. At what rate is water being poured into the cup when the water level is 8 centimeters? So the thing to be aware of here, they're basically saying, in this case, that the water level is rising at a constant rate. But what that means is, because the cone gets wider as you go up, they're going to have to put the rate at which water is being poured into the cone to keep the rate constant is going to have to continually increase because the cone gets continually wider as you go up. And that's the secret to calculus. Anytime you have a physical situation in which every little iota of time goes by, something changes a little bit, that's when it's time to use calculus. So let's draw a picture. So step one, here's my super system. Just follow my steps. It'll work every time. Step one, draw picture. I think you can all do step one. So I'm going to give us a big fat cone over here. Okay, and we're going to put in the numbers they gave us. They say this thing has a height of 10 centimeters and also a radius of 10 centimeters. Okay, so the idea is we're pouring water in, and here's the water level. And yeah, you can see that as the water level rises, you know, the circumference of the circle that the water level is on gets bigger. So you're going to have to pour water in at a faster and faster rate to keep that rate, the height of that water rate, rising at a constant rate. Okay, congratulations. We've completed step one of the super system. Let's move on to step two, which is write down the relevant equation. So on every related rates problem, once you draw your picture, the next thing you want to do is try and figure out what equation they're asking you to write down. There's always going to be a blatant one that they want you to write down. It's usually an area or a volume, okay? So if it's usually an area or a volume, what do you think the relevant equation would be for this problem? Pretty obviously, I think it's the volume of the cone. Okay, so that's what you want to do for step two. Just think about what equation are they asking me blatantly to write down. It's usually an area or volume. It's usually pretty obvious. So this is a cone problem. We want the volume of the cone. So hopefully you know that the volume of a cone is 1/3 pi r squared times the height. Okay, so step three. That's our relevant equation. But you'll notice there's too many variables. We have a v as a variable, an r as a variable, and an h as a variable. So that's too many. So step three is eliminate a variable using the initial, I'll say initial conditions. But basically we want to eliminate one of the variables using something about the problem that they gave us already. Okay, so what do they give us about the problem? So we know this thing has a radius of 10 and a height of 10, right? So as this thing fills up, basically that ratio is going to remain a constant. Okay, so I want to write r in terms of h. That's what I mean by getting rid of a variable. So when the water's like here, say, oh shoot, let me draw that again. when the water's like here, it's going to have some R and some H. But those are the proportion of R to H is going to remain constant as this thing fills up. And we know that R is 10 and H is 10 when the thing is totally full. This is what I mean by initial conditions. So we know that this cone, that R is equal to H, right? The radius is 10 centimeters and the height is 10 centimeters when it's totally full. And that ratio will stay the same no matter what height the water's at. The radius will always equal the height, okay? So that's how we eliminate a variable using the initial problem conditions. So which one? So we could get rid of R or H, but this problem is asking for at what rate is the water being poured into the cup? Well, let's see. We know that the water level rises at a rate of 2 centimeters per second, so that's a height. I can get rid of R. We want to know something about the height, okay? So plugging in, we have volume equals 1/3 pi. I'm going to replace R with H. To get volume equals 1/3 pi H cubed for this particular cone. Okay. Step 4. Take the derivative with respect to time on both sides of the equation. Okay, so we're doing related rates. What is a rate? A rate is something that changes in time. So on all these problems, you're going to be taking a derivative with respect to t time. Okay, so that's what a rate is, something changing in time. Every little bit of time that goes by, something's a little bit different. Okay, so we're going to take the derivative of both sides of this equation with respect to t to get dv dt equals 1/3 pi. Okay, our variable is h. So h in this case is a function of time, right? Because as time goes on, the height of the water is increasing. So I want you to think back to the implicit differentiation section that you just did. That's the last video I sent out. Review it if you need to. But h, we're going to call some function of time that we don't know. So we're going to do an implicit differentiation, which is really the chain rule in disguise. Okay, so looking at the h cubed, we do the regular old power rule. The 3 comes in front. Times h squared, right? That's the power rule. Times the derivative of the inside function. dh dt. Okay? So I use implicit differentiation. Again, h is some function of time that we don't know. So just pretend h is like some function with t's in it. We're using the chain rule or implicit differentiation, kind of the same thing. Okay, so one more time, this is probably the trickiest part. We're taking the derivative of this h cubed here, right? So we're using the power rule, chain rule with the power rule. So power rule says the exponent comes out in front, right? So the 3, that's this 3 here. We leave the inside function plugged in, which is just h in this case, and subtract 1 from the exponent to get squared here. And then we do the times the derivative of the inside function, which we're just going to call dh dt, okay, because we don't know how h depends on time. But here's the cool thing. Okay, we have completed step 4. We've taken the derivative of both sides, and we're left with this equation. Now let's go back to the problem. What is it asking for? The cup is being filled with water, so the water level rises at a rate of 2 centimeters per second. That is the rate that the h, the height, is changing. That's dh dt, right? That's this guy here. That is the rate that the dh dt, the water, is changing. So we know from the problem's always going to give you one of these. So you're always going to end up with 2 derivatives when you take the derivative of both sides. So you can see we have this one and this one. And the problem is always going to give you one of them and ask for the other. Okay? So they gave us the rate that the height is changing, dHdt, is a constant, right? So we know that. And what's the problem asking for? At what rate is water being poured into the cup when the water level is 8 centimeters? So the rate that water is being poured into the cup, that is the rate that the volume is changing, right? And that's dV dt. See that when you end up with the two derivatives, when you take the derivative of both sides, one of them they will give you in the problem, and the other one they will ask you to solve for. Okay, so we want dV dt equals these threes cancel, so we get pi. H, we want to know at when, because it's always changing, right? At what rate is water being poured into the cup? Exactly when the height is 8 centimeters, because in order to keep that height moving up at a constant rate, you're going to have to pour water in at a faster and faster rate. Every little instant of time that goes by, the rate that you're pouring water in slightly increases. That's your classic calculus moment. So we know that H is whatever I just said it was, 8 centimeters, right? So we get 8 centimeters squared. dH dt, which we just agreed was 2 centimeters per second. Okay, very good. So we are ready to solve the problem. The rate that water is being poured in the cup, dV dt, equals pi times 64 centimeters squared times 2 centimeters per second to get, I'm just going to leave it in terms of pi, 128 pi. Let's make sure our units make sense. Centimeters cubed, that's a volume, per second, that's a rate. That is the answer. Okay. I swear these steps work every time. It's awesome. So I'm just going to recap real quick before I send you away. Again, draw a picture, always the first step. Write down the relevant equation. Again, what I mean by that is the question is going to just blatantly be asking you to write down an equation, usually an area or a volume. This problem had a cone, so it's the volume of a cone. Sometimes it's a circle, like a water spill or something. That's in a circle, like an oil spill is a common one. What do you think they're asking for there? It's the area of a circle, pi r squared. Okay, write it down. So volume equals 1/3 pi r squared h. Many times, not every time, you need to eliminate one of the variables using the initial conditions of the problem. Okay, so we have too many variables, v, r, and h, but they told us that this cone is 10 by height of 10 with a radius of 10. That remains constant. In other words, no matter what the height, it's always going to equal the radius. So we're able to say in this case that r equals h. That allows us to eliminate a variable. Which one? Well, they're asking about h, not r, so I want h's. So we plug this in to eliminate a variable. Then we have v equals 1/3 pi h cubed. Okay. Step 4 is always take the derivative with respect to time of both sides of the equation using implicit differentiation. Okay, which is really the chain rule in disguise. So again, h is a function of t that we don't know. So we take the derivative of both sides, use your implicit differentiation, and the resulting equation will have two derivatives in it with respect to time. One of them will be the rate that they're asking for, and one will be a rate that they gave you in the problem. Plug them in, and you'll get the answer. It works every time. Don't hesitate to reach out with questions. Good luck.